Welcome to ilectureonline. In this set of videos, we're going to learn how to integrate trigonometric functions. Here we're going to start with the sine and the cosine. What is the integral of the cosine of x and what is the integral of the sine of x? Since integration is the reverse of differentiation, let's first go back to something we're familiar with. What is the derivative with respect to x of the sine of x, and what is the derivative of cosine of x with respect to x? Well, the derivative of the sine of x is equal to the cosine of x, and the derivative of the cosine of x is equal to the negative sine of x. That means if we then do the integration, we can go backwards, which means if we integrate the cosine of x, we should get back the sine of x, and if we integrate the sine of x, we should get back the inverse or the negative of the cosine of x. I shouldn't say inverse, but the negative of the cosine of x. Let's see why that works. If we come over here, you see that we have a cosine curve and we have a sine curve. And the derivative of a cosine curve, they claim here, that is the negative of the sine curve. Let's see if that works. Here, if we take the derivative of the cosine, we should get 0, because the derivative of a function is equal to the slope of the function, and the slope of the cosine right there is 0, and that's indeed what we get. The sine of x is 0, so that seems to make sense. If we now come over here, we can see that the derivative of the cosine of x should give us a negative quantity. It's a negative slope. But the sine is positive. Also, we can see that that's where the slope is the steepest, which means that's where the sine function should be the largest, and it is. It's its very peak right here. It's the maximum value for the sine of x at this particular location. If we work on the unit circle, we can say that the sine of x will be equal to 1 there. That means the slope here will be a negative 1. But you can see that if we take the derivative of the cosine of x, right here, we get the negative sine of x, which makes sense because it's a negative slope. Since sine of x is positive here, take the negative of that, we get negative 1, which indicates what the slope is. If we come down here, there's the cosine of x. If we take the derivative of the cosine of x over here, we should get 0, and that is indeed the case again there. If we look at this point right here, if we take the derivative of the cosine of x at this point, we should get plus 1. But the sine of x is minus 1 here, but if you put a negative in front of it, we get plus 1 again, that matches. So you can see that the cosine and the sine of x are the derivatives of each other, or the negative of the derivative of the other. If we then take the integral, we simply then go backwards. If the derivative of the sine of x is equal to the cosine of x, the integral of the cosine of x therefore must equal the sine of x. We should also add a constant of integration, because when we take the derivative, if for example we had the derivative of the sine of x plus 5, then the 5 would drop off and we have no visibility that there was actually a constant there. So whenever we integrate, we must always indicate that there might have been some constant that was there when we took the derivative that we have no knowledge of, so we just go ahead and put in that constant. For the sine of x, notice that if we take the derivative of the cosine of x, we get the negative sine. Therefore, if we integrate the sine, we should get the negative cosine back. So the minus the cosine of x, and again, plus a constant of integration, because if we took the derivative of a constant, it goes to 0, and we have no knowledge of it. So that's how we do the integrals of both the cosine and the sine, and that's a good start for learning how to integrate trigonometric functions. On the next video, we'll go ahead and show you how we actually know that this is true by expanding the sine and the cosine into an infinite series. Take the derivative and then take the integral back and see that that relationship is there. So stay tuned if you want to know more about how to integrate trigonometric functions. In this video, we're going to find the integral of the sine and the cosine using the infinite expansion for the sine and the cosine. So the sine and the cosine can be written like this. Now let's find the integration of that. Starting with the, let's start with the cosine. We're going to integrate the cosine of x times dx, and that is equal to the integral of the quantity 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus and so forth, all times dx. All right, let's integrate it one term at a time. This is equal to the integral of 1 becomes x minus the integral of x squared is x cubed divided by the new exponent 3 times 2 factorial plus x to the 5th power divided by the new exponent 5 times 4 factorial minus x to the 7th power divided by 7 times 6 factorial and so forth. And of course, we can't forget the constant of integration. Now, in this case, it looks like if we let c equal to 0, and we're perfectly fine to do that, then we can go ahead and say this is equal to x minus x cubed over, this becomes 3 factorial, plus x to the 5th over, and that becomes 5 factorial, minus x to the 7th over 7 factorial, and so forth. And if you look at this, come back over here, that looks exactly like the sine of x, so this is therefore equal to the sine of x. The sine of x is the integral of the cosine of x. Now let's try the integration of the sine of x. When I integrate the sine of x dx, this is equal to the integral of, and since the sine of x is equal to that, I can go ahead and repeat that. That would be x minus x cubed over 3 factorial. Let me draw a line here so it's a little bit clearer what we're doing. Plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus and so forth, and the whole thing multiplied times dx. All right, now we'll integrate each individual term. We get the following. This is equal to x squared over 2 minus x to the 4th over 4 times 3 factorial plus x to the 5th, oh no, that's x to the 6th divided by 6 times 5 factorial minus x to the 8th over 8 times 7 factorial and so forth. And I don't need the parentheses, but I still need a constant of integration. In this case, let c equal 1, because when I integrate the sine of x, I should get back to this 1 over here. So I'm going to let c equals 1. When I do that, and let me come over here, because I have more room on this side of the board. I'll put the 1 first. I get is equal to 1 plus x squared over, let me put the equal sign there. Actually, you know what? I think I'm going to let c equal negative 1. Yeah, remember the trick here. Let c equal negative 1. This equals negative 1 plus x squared over 2 factorial, because 2 is the same as 2 factorial, minus x to the 4th over 4 factorial, because 4 times 3 factorial is 4 factorial, plus x to the 6th over 6 factorial, minus and so forth. Now, notice that that is exactly the negative of the cosine of x, because all the signs are reversed. Instead of a positive 1, I have a negative 1. Instead of a negative x squared over 2 factorial, I have a positive x squared over 2 factorial and so forth. So it looks like this is equal to the negative of the cosine of x, which means if I integrate the sine of x, I get back the negative cosine of x. And if I integrate the cosine of x, I get back the sine of x. And so we've shown through integrating the infinite expansions of the sine and the cosine, I get back what I expected, just like on the first video. When I integrate the cosine of x, I get the sine of x. When I integrate the sine of x, I get the negative cosine of x. And that's how it's done. In this video, instead of finding the integral of the sine of x and the cosine of x, we're going to find the integral of the sine of ax and the cosine of ax. It's a technique that we need to learn how to use in the case of doing integrals of trigonometric functions. What we need to do here is substitute ax for something else. What we're going to do here is we're going to say let u equals a times x. That means that du dx, if we take the derivative of that with respect to x, we get a. That means du equals a times dx, or dx is equal to du divided by a. So what we're going to do is we're going to replace ax by u and dx by du divided by a and see what we get. So this becomes the integral of the sine of u, and instead of writing dx, we're going to write times du over a. We can then take the a outside integral sign, so this is equal to 1 over a times the integral of the sine of u times du. This we know how to integrate. Instead of u, we know how to do it with x. It doesn't make any difference what the variable is. So the integral of the sine of u is equal to the negative cosine. This is equal to 1 over a times the negative cosine of u plus a constant of integration. All we have to do now is replace u back for ax. And so what we can then write is, and probably I'll get rid of this in a moment, this is equal to minus 1 over a times the cosine of ax plus the constant of integration. And that would be the integral of the sine of ax dx. All we have to do here is use simple substitution. Now we're going to integrate the cosine of ax, the cosine of ax dx. And again, we use the exact same substitution. We let u equals ax, and therefore dx becomes du over a. So this can now be written as the cosine of u, and instead of dx, we're going to write du over a, which means we can bring the 1 over a out of the integral sign. We get the integral of the cosine of u times du. And then we can integrate this. This is equal to 1 over a times the sine of u, but we still need a constant of integration. And finally, we replace for u back ax, what u is equal to. This is equal to 1 over a times the sine of ax plus a constant of integration. And this is the integral of the cosine of ax dx. So if we have, other than an x, just a simple angle, a constant times the angle, we need to use the method of substitution to come up with the proper integrals. And that's how it's done. Now let's take a look and see how to integrate the tangent of x. The best way to do that is to change the tangent of x into what it's equal to. We can write this as the integral of the sine of x divided by the cosine of x times dx. Now you need to realize that the sine of x is related to the cosine of x in such a way that if you take the integral of the cosine of x, you get the negative sine of x. So it looks like we have the differential here, and if we then write it as this, if we say let u equal what's in the denominator, the cosine of x, then we can say that du dx is equal to the negative sine of x, and so du can be written as a negative sine of x times dx, or dx can be written as du divided by the negative sine of x. Now, how do we substitute that back in? Well, let's see. We can write this as the integral of the cosine of x can be written as u. So in the denominator we write u. In the numerator we have the sine of x times dx. And let's take a look over here. The sine of x times dx times the negative is equal to du. So if we multiply both sides of that by a negative, we get minus du is equal to the sine of x times dx. This can now be replaced by the minus du. So this can now be written as the integral of minus du divided by u. And then if we take the negative outside, this can be written as minus 1 times the integral of du over u. And now we can go ahead and integrate this because that's equal to the natural log of u. This is equal to minus 1 times the natural log of u. And then if we replace what u is equal to, we can go back over here and say this is equal to minus 1 times the natural log of the cosine of x, the cosine of x. And now if we use the rules of logarithms and we bring that over here, we can write this as the natural log of the cosine of x raised to the minus 1, which is equal to, I'll come over here now, continue, which is equal to the natural log of 1 over the cosine of x. And then finally, 1 over the cosine of x is equal to the secant of x. So this can now be written as the natural log of the secant of x. I dropped the absolute value signs because we know that there's certain limits to the secant of x. We just need to make sure that we know how to integrate that. So it turns out that the tangent of x dx can be written as the natural log of the secant of x. Ooh, but one more thing. We, of course, also have to add a constant of integration, which I neglected to do. So let me plug in plus c, plus c, plus c, and plus c. We can't forget about the constant of integration. The integral of the tangent of x is equal to the natural log of the secant of x plus a constant of integration. And that's how it's done. Now let's take a look and see how we find the integral of the cotangent of x. Again, just like with the tangent of x, we're going to write it as follows. This can be now written as the integral of the cosine of x divided by the sine of x times dx. And again, we have to realize that the differential of the sine of x, and I forgot my x down here, the sine of x is the cosine of x. So if we use the following substitution, let u equal the denominator, the sine of x, then we can say that du dx is equal to the cosine of x, or du is equal to the cosine of x dx. And I think that's as far as we need to go, because notice if we let the denominator be u, then the numerator, the cosine of x dx, is equal to du. So that means we can write the integral as follows. This is equal to the integral of, in the denominator, the sine of x will be replaced by u. In the denominator, the cosine of x dx can be replaced by du. And we know that the integral of du over u is equal to the natural log of u. Since u is equal to the sine of x, we can say, oh yes, I can't forget my plus c. And since u can be written as the sine of x, this is equal to the natural log of the sine of x plus a constant of integration. That is the integral of the cotangent of x. And that's how we do that. Just to make sure that we know how to handle one of these, when we have a constant in there for the angle, we'll do one more example like this. Take the integral of the tangent of ax. What we need to do is rewrite it as the integral of the sine of ax divided by the cosine of ax times dx. Again, we need to use a substitution. Let u equal what's in the denominator. In this case, that's going to be equal to the cosine of ax. And then we can say that du dx, the derivative of that, is equal to, the derivative of cosine is a negative sign, so it's a negative, the sine of ax times the derivative of the angle times a. In other words, we can write du as being equal to minus a times the sine of ax times dx. And that's as far as we need to go, because now we can come over here and make the substitution. This is equal to the integral of the sine of ax dx divided by the cosine of ax can now be written as u. Now take a look at the numerator. The sine of ax dx is this portion right here. What we don't have is we don't have a minus a. All right, what we can then do is say that du, or what we can say here is that the sine of ax dx can be written as du divided by a minus a. So we're going to replace what's in the numerator by du over minus a. This can now be written as the integral of du over minus a times u. And since a is a constant, we can move that to outside integral sign. This can now be written as 1 over, or minus 1 over a, times the integral of du over u. And now we can go ahead and integrate that. That is equal to minus 1 over a times the natural log of u plus a constant of integration. Can't forget about that. Now what we can do is replace u by what u is equal to. This is equal to minus 1 over a times the natural log of the cosine of ax. We can also take the negative sign and move it up here. This can now be written as 1 over a times the natural log of the cosine of ax raised to the minus 1 power, which is equal to 1 over a times the natural log of 1 over the cosine of ax. Oh, I keep forgetting my plus c's, don't I? Yes. Next, what we can say is that 1 over the cosine of ax must be equal to the secant of ax. So this is equal to 1 over a times the natural log of the secant of ax plus a constant of integration. And essentially, this is the correct form of the integral of the tangent of ax. So that's how you see how things change a little bit when you have a constant in front of the x, and that will then be the final answer of that. And that's how we do that. Here we're going to try to find the integral of the secant square of x. Now actually we're going to do it kind of walking through the back door in a way. What we're going to try to do here is try to find the derivative of the tangent of x and try to relate that to the secant square of x. So kind of doing things backwards a little bit, but sometimes backwards works just fine. So what if we do this? We take the derivative, the dtx, of the tangent of x. Let's see what we get. Well, that would be the derivative, the d dx, of the tangent can be written as the sine of x divided by the cosine of x. And that's a quotient, so now we're going to use the quotient rule. This is equal to the denominator, cosine of x, times the derivative of the numerator. The derivative of the sine is the cosine of x, minus the numerator, which is the sine of x, times the derivative of the denominator. Now the derivative of the cosine of x is the minus sine of x. And the whole thing divided by the denominator squared, cosine square of x. That can be simplified to the cosine times the cosine is the cosine square of x, and the minus times the minus is plus, and the sine times the sine is the sine square of x divided by the cosine square of x. In the numerator, everybody should recognize that the cosine square plus the sine square is equal to 1. This is equal to 1 divided by the cosine square of x. And 1 over the cosine is equal to the secant, therefore 1 over the cosine square is equal to the secant square of x. This is equal to the secant square of x. What we're seeing here is that if we take the derivative of the tangent of x, we get the secant squared of x, which means that if we take the integral of the secant square of x, the integral of the secant square of x dx, we get back the tangent of x. Right here, we get back the tangent of x, of course, plus a constant of integration. So that's one way in which we can figure out the integral of the secant squared of x, by recognizing that if we take the derivative of the tangent, we get the secant square. Therefore, the integral of the secant square gives us back the tangent of x. And that's how we do that. Here's the same problem again as in the previous video, but here we're going to attack it in a slightly different approach. How do you find the integral of the secant squared of x dx? What we're going to do here is we're going to make a substitution. We're going to let u equal the tangent of x. If we do that, then du dx, the derivative of that with respect to x, is equal to, well, the tangent of x, of course, is the sine of x divided by the cosine of x. So here, when we take the derivative, that would be equal to the denominator, cosine of x, times the derivative of the numerator, which is the cosine of x, minus the numerator, which is the sine of x, times the derivative of the denominator, which is the minus sine of x, all divided by the denominator squared. That's the cosine square of x. This simplifies to the cosine square of x, and minus times the minus is a plus, sine square of x divided by the cosine square of x. The numerator then, of course, simplifies to 1. This is equal to 1 over the cosine square of x, which is equal to the secant square of x. du dx is equal to the secant square of x, or du is equal to the secant square of x times du. If you take, not du, but dx, because I'm moving the dx over. If you look at the numerator, if you look at this here, and you look at this, you say, well, that's exactly the same, which means I can write this as the integral of, instead of writing secant square of x dx, I can simply write du. And of course, that's the easiest integral in the world. The integral of du is simply equal to u plus a constant of integration. And then u, since u was equal to the tangent of x, I can then say this is equal to the tangent of x plus the constant of integration. The integral of the secant square of x dx is equal to the tangent of x plus the constant of integration. Again, it does take some priority knowledge of the trick that we need to use, realizing that the integral of the secant square of x is indeed the tangent of x, and that is what proves it. And that's how we do it. In this video, we're going to try to find the integral of the cosecant square of x. And if you learn anything from the previous video, we might have a hint. How about doing the following? Let u equal, instead of the tangent of x like we did in the previous video, we're going to try the cotangent of x. In that case, of course, the cotangent of x is equal to the sine, not the sine, it's equal to the cosine of x divided by the sine of x. And then if we take the derivative of that, du dx, with respect to x, that is equal to the denominator, sine of x, times the derivative of the numerator. The derivative of cosine is the negative sine, minus the numerator, times the derivative of the denominator, which is the cosine of x, all divided by the denominator squared. We can simplify that. We can write this as du dx is equal to the negative sine square of x minus the cosine square of x, all divided by the sine square of x. And then in the numerator, if I factor out the negative 1, du dx is equal to minus 1 times the sine, that's the sine here, the sine square of x plus the cosine square of x. The whole thing divided by the sine square of x. And of course, the sine square of x times plus the cosine square of x is equal to 1. So we see that du dx is equal to minus 1 divided by the sine square of x, which is equal to minus the cosecant square of x. If I now multiply both sides by a dx, I get du is equal to minus the cosecant square of x times dx. Or, if I multiply both sides by negative 1, I can write minus du is equal to the cosecant square of x times dx. The reason why I did this last step is because when I look up here, I see the cosine square of x dx, which is equal to minus du if I let u equal the cotangent of x. So substituting that in, I get this is equal to the integral of minus du. The minus can come outside integral sign. This is minus 1 times the integral of du. And of course, that's the easiest integral in the world. The integral of du is equal to u minus 1 times u plus a constant of integration. And since u is equal to the cotangent of x, this is equal to minus the cotangent of x plus a constant of integration, which is the integral of the cosecant square of x dx. Again, the way we solve this is to kind of suspect that that's the case, and then we simply make the substitution, let u equals the cotangent of x, and that's how we solve a problem like this. Here we're going to try to find the integral of the cosine square of x. Now, over here on the right side of the board, notice that we have some very handy identities. In the case of doing trigonometric integrals, or integrals of trigonometric functions, I should say, it is really handy to have very close to you the identity of the sine square of x and the cosine square of x. Notice the sine square of x can be written as 1/2 times 1 minus the cosine of 2x, and the cosine square of x can be written as 1/2 times 1 plus the cosine of 2x. What that does is it allows you to take a function which is squared and replace it by a function which is to the first power, which is a lot easier to integrate. So notice here that if we then replace the cosine square of x by its identity, it looks as follows. This is equal to the integral of 1/2 times 1, in the case of the cosine, it's plus the cosine of 2x times dx. Now we can take the 1/2 outside the integral sign, and we can split it up into two different integrals. So this can now be written as 1/2 times the first integral, which would be 1 times dx, plus the second integral, which would be the cosine of 2x times dx. Now this is an easy integral to integrate, but here we have to be careful because we have the cosine of 2x dx, which means we need the differential of 2 times dx. If we let u equals the cosine of 2x, the differential or the derivative would be the negative, well, let's see, no, that would be the sine of 2x times 2 dx, so we need a 2 in there. So what we're going to do next is write this as 1/2 times the integral of dx plus, this is now going to become the cosine of 2x, and we need an extra 2 in there. Let me use a different color. We need a 2 in there. So if we multiply this by 2, we also have to divide it by 2, so we keep everything the same. Looks like this pen is dying on me. And we need to close the brackets. So now we have the proper differential 2 dx, so we can integrate this. That's where the extra 1/2 came from. Now we can go ahead and integrate both integrals. This is equal to 1/2 times, the integral of dx would be x, plus 1/2 times, the integral of this would be the integral of this, the cosine is the sine of 2x times, not times anything, it's simply the sine of 2x, and then we simply also have to add the constant of integration. Never forget the constant of integration, like I do quite often. Simplifying this a little bit more, this can now be written as 1/2 times x plus 1/4 times the sine of 2x plus a constant of integration, and that would be the integral of the cosine squared of x dx. And that's how we do that. Quite tricky, isn't it? So these, keep them very handy, because those will come in handy in a lot of these kinds of examples. Whenever you have the cosine square, the sine square, or the cosine or the sine to even a higher power, that will be the key to helping us figure out how to do the integral of those functions. That's how it's done. Here, in our example, here we have the integral of the sine square of x dx. And just like in the previous video, we're probably going to use these two identities, at least one of those two identities. Notice that the sine square of x can be written as 1/2 times 1 minus the cosine of 2x. And when we do that, what that does is it changes an equation or a function that is to the second power into a function that's down to the first power, and that's a lot easier to integrate. So let's try that. Let's try that identity swap. We're going to now integrate. Instead of saying the sine square of x, we're going to now make it 1/2 times 1 minus the cosine of 2x dx. Now notice we can take the 1/2 outside the integral sign. This is equal to 1/2 times the integral of, and we can separate that into, well, let's write it like this first. 1 minus the cosine of 2x times dx. And then we can separate this into two separate integrals. So this can be written as 1/2 times the integral of 1 times dx minus the integral of the cosine of 2x times dx. Notice I left a little bit of room there, because I realized that if I want to integrate the cosine of 2x, I need a 2 dx here. So grabbing my other pen here, I need a 2 dx. Of course, if I multiply this times 2, I also have to divide it by 2 to compensate for that. So now I can go ahead and integrate the cosine of 2x. Continuing on, this is equal to 1/2 times the integral of dx is x minus 1/2 times the integral of the cosine of 2x times 2 dx is equal to the sine of 2x. We can't forget the constant of integration. Now simplifying this, this is equal to 1/2 times x minus 1/4 times the sine of 2x plus a constant of integration, and that is the integral of the sine square of x dx. Again, notice that if we use the substitution there for the sine square of x into something, a function that is only to the first power, it makes it a whole lot easier to integrate. And that's how we do that. Here we have something slightly different. Here we're trying to find the integral of the cosine cube of x dx. Here we need a different trick. Notice I've added some additional identities here that may come in handy. The sine square of x plus the cosine square of x equals 1. And therefore, we can then write the cosine square of x equals 1 minus the sine square of x. The reason why I did that is because we can take this integral and make it look like this. This is equal to the integral of the cosine of x, or yes, times the cosine square of x times dx. Notice I can then take the cosine square of x and make it look like this, 1 minus the sine square of x. And the reason why I'm doing that is because sometimes one of the functions, the cosine, can become the differential of the sine, or the sine can become the differential of the cosine. See in just a moment what I mean with that. So we're going to replace the cosine square of x by 1 minus the sine square of x. This is equal to the integral of, instead of cosine square of x, I write 1 minus the sine square of x. I still have my cosine of x, I'm going to write that there, times dx. Now the reason why I replaced them like that is because, well, you'll see in just a moment why I did that. I'm now going to multiply this times each of the two terms. This is equal to the integral of the cosine of x minus the sine square of x times the cosine of x times dx. And now I can write it as two separate integrals. This is equal to the first integral, which is the cosine of x dx, which is easy to integrate, minus the integral of the sine square of x times the cosine of x dx. And notice that the derivative of the sine of x is the cosine of x, so therefore the differential of the sine of x is the cosine of x dx. In other words, for the second integration right here, I'm going to let u equal the sine of x. Therefore, du dx is equal to the derivative of the sine, which is the cosine of x, or du is equal to the cosine of x dx. In other words, if I let u equal the sine of x, then du is equal to the cosine of x times dx, which is what I have over here. This here would be our du, and then u would be the sine of x, so the sine square of x would be u squared. The following integrals become now I get the following. This is the cosine of x dx minus the integral of u squared times du, and this I know how to integrate. The first one is also easy. The integral of the cosine would be equal to the sine of x minus the integral of this is u cubed over 3. And of course, I can't forget the constant of integration. Now I have to plug back in what u is equal to. U is equal to the sine of x. So this becomes the following. The integral of the cosine cube of x is equal to the sine of x minus u, which is sine of x. So that would be the sine cube of x divided by 3 plus a constant of integration. And this then would be the integral of the cosine cube of x. So once you know the trick, write it like the cosine of x times the cosine square of x, and then replace the cosine square of x by 1 minus the sine square of x, realizing that the cosine of x is the differential of the sine of x. And that's how we do that. In this video, we're going to try to find the integral of the sine cube of x. And we're going to use the same trick we did in the previous integral when we tried to find the cosine cube of x. So for that, we have these relationships that the sine square of x plus the cosine square of x equals 1. That means we can also write the sine square of x as 1 minus the cosine square of x. And this we're going to use as a technique to solve for this integral right here. Because what we're going to do is we're going to separate the sine cube of x into the sine square of x times the sine of x times dx. And then we're going to replace the sine square of x by 1 minus the cosine square of x. Again, the reason why we do that is because we realize that the sine of x is the differential of the cosine of x. So we're going to replace the sine square of x by 1 minus the cosine square of x, and multiply that times the sine of x times dx. Now we're going to multiply the sine of x through with these two terms here. This gives us the integral of the sine of x minus the cosine square of x times the sine of x, the whole thing times dx. And now we have two separate integrals. We can separate those. This can now be written as the integral of the sine of x times dx minus the integral of the cosine square of x times the sine of x times dx. Now when we let u equal the cosine of x, see what happens. Let u equal the cosine of x, then du dx is equal to minus the sine of x, and du is equal to minus the sine of x times dx. So we need a minus sine of x dx. I look over here, and I have a sine of x dx, so I need a minus sign, which is over here. I can then rewrite this as follows. This is equal to the integral of the sine of x dx plus the integral of the cosine square of x times a minus sine of x times dx. And notice now I have the exact differential du, and I'll let the cosine of x equals u, so the cosine square of x is u squared. This can now be written as the integral of the sine of x times dx plus the integral of u squared du. This is easy to integrate. We know that the derivative of the sine of x is the cosine of x, so the integral of the sine of x is the negative cosine of x. This is equal to the negative cosine of x plus, when I integrate u squared, I get u cubed divided by the new exponent 3, and I can't forget my constant of integration. Now replacing u by what u is equal to, the cosine of x, this is equal to minus the cosine of x plus the cosine cube of x divided by 3 plus a constant of integration, and that is the integral of the sine cube of x dx. Now notice again, we needed to use some trick here. Once we use a trick, the rest is easy. If you've never seen this before and you can't figure out the trick, it may be quite hard to try and figure out how to integrate this. Once the trick is down, it's pretty easy after that. And that's how we do that. With these types of problems, it's all about knowing what trick to use to figure out how to find the integral of something like this. If you don't know the trick or you can't figure it out, it makes it very difficult to find out the solution to this. Well, the trick here is to rewrite the sine to the 5th power of x as follows. We're going to rewrite this as the integral of the sine to the 4th power of x times the sine to the 1st power of x times the cosine square of x times dx. Now the sine to the 4th power of x, that can be written as follows. This is equal to the integral of the sine square of x, quantity squared, times the sine of x times the cosine square of x times dx. The reason why we did this is because we want to take the sine square of x, come over here and replace it by 1 minus the cosine square of x. When we do that, we get the following. This is equal to the integral of 1 minus the cosine square of x, quantity squared, times the sine of x times the cosine square of x dx. Now the next step is to multiply this out. Again, the whole idea is to find the differential of one of them. And since now we have the cosine square of x squared, and we have a cosine square here, we have a sine here. The sine is the differential of the cosine. So notice what we're going to do next. This is equal to the integral of, working this out, this is 1 minus 2 times the cosine square of x plus the cosine to the 4th of x. We're now going to write this one next, cosine square of x times the sine of x dx. Now we'll multiply this through with each of the 3 terms in here. This is equal to the integral of the cosine square of x minus 2 times the cosine to the 4th of x plus the cosine to the 6th of x, all multiplied times the sine of x dx. Now notice that the differential of the cosine of x is equal to the sine of x. Is it the positive or the negative sine of x? Well, let's find out in just a moment. Let u equal the cosine of x, then du dx is equal to the derivative of cosine is the negative sine of x. Thus the du is equal to minus the sine of x times dx. It's a negative sine of x dx, and we have a positive sine of x dx. So what we need to do is make that into a negative. That means if we change all the signs here and make that into a negative, we get the following. This is equal to the integral of the negative cosine square of x plus 2 times the cosine to the 4th of x minus, that's an x here, minus 6 times the cosine to the 6th of x times a minus sine of x dx, which is the exact same thing as du. In each of these, the cosine of x can be replaced by u, so this whole thing can now be written as the integral of minus u squared plus 2 times u to the 4th minus 6 times u to the 6th. Oh, wait a minute, I don't have a 6 there. Oh, let's get rid of that. That looked kind of strange, didn't it? Okay, and then multiply the whole thing times, this will now be a du. And this is fairly straightforward to integrate. Let's go ahead and do that. This is equal to minus u cubed over 3 plus 2u to the 5th over 5 and minus u to the 7th over 7 plus a constant of integration. Can't forget about that. Now we plug back in what u is equal to. Since u is equal to the cosine of x, this is equal to minus the cosine cube of x divided by 3 plus 2 times the cosine to the 5th of x over 5, oh, not plus, but minus the cosine to the 7th of x divided by 7 plus a constant of integration, and that would be the integral of the sine to the 5th of x times the cosine squared of x dx. Wow, without that trick, without realizing that we can write the sine to the 5th of x as this, then write this as the square of the sine squared of x, then make the replacement. The sine squared of x is 1 minus the cosine squared of x. Then combine all the cosine terms, realizing that the sine of x makes a differential for the cosine of x. Of course, we need a negative sign. We change all the signs in here to compensate for that. And then we get the final answer. Once you know the trick, it's not that hard. And that's how we do it. Our next example is the integral of the sine to the 4th power of x dx. How do we figure that out? Well, again, it all depends on finding the right tricks to do this. We need to simplify this as much as possible. So what we can start out doing is probably the following. Write this as the integral of the sine of x, or the sine square of x, quantity squared times dx. Now what we can do here is take this and find the proper identity. The sine square of x can be written as this. So let's make that substitution. This can now be written as the integral of 1/2 times 1 minus the cosine of 2x. And the whole thing squared, because we still have this quantity squared. So the sine squared of x becomes this, squared times dx. We can square the 1/2, take it to the outside. So this is equal to 1/4 times the integral of 1 minus the cosine of 2x squared times dx. And now if we square this, we get the following. Again, what we're trying to do here is make it as simple as possible so we have everything to the 1st power. That makes it easier to integrate. This is equal to 1/4 times the integral of, squaring this out, you get 1 minus 2 times the cosine of 2x plus the cosine squared of 2x times dx. The only thing we have left is we have the cosine square of 2x here. We can again simplify that. Let me write that over here. If we have the cosine square of 2x, that is equal to, now come over here, we have the cosine square of x is equal to this. So that means it's equal to 1/2 times 1 plus the cosine of 4x. Notice that we double the angle and everything else looks exactly the same, which means when we come over here, we can take this quantity here and write it like that. Let's go ahead and do that. This is equal to 1/4 times the integral of 1 minus 2 times the cosine of 2x plus, instead of writing the cosine square of 2x, we write 1/2 times 1 plus the cosine of 4x, and the whole thing times dx. Okay, now we need to simplify this a little bit more. This is equal to 1/4 times the integral of, here we have 1 plus 1/2, that makes it 3/2, minus 2 times the cosine of 2x, and plus 1/2 times this, plus 1/2 times the cosine of 4x. Put parentheses around that, times dx. And now we're about ready to start integrating this. Let's write this as 3 separate integrals. Come over here. And this is equal to 1/4 times. The first integral would be 3/2 times dx, minus the second integral would be 2 times the integral of the cosine of 2x times dx. And I left a little room here for a reason. Plus 1/2 times the integral of the cosine of 4x dx. And again, I left a little bit of room here for a reason. The reason why I left room is because if you want to integrate the cosine of 2x, you need a 2dx here. And if you want to integrate the cosine of 4x, you need a 4dx there. Using a different color so you can see what I'm doing. We need a 2dx. Of course, when we multiply times 2, we have to divide by 2. Here we need a 4x. When you multiply times 4, you have to divide by 4. You need to do that. Now we're ready to integrate all 3 of the integrals. This is equal to 1/4 times. The integral of dx is x. That would be 3 over 2x minus 2 divided by 2 is 0, of course. The integral of the cosine. Remember, the derivative of the sine is the cosine, so the integral of the cosine is the sine. You get the sine back, so minus the sine of 2x, and here plus 1/8. The integral of the cosine would be the sine, so that would be the sine of 4x, and we still have a constant of integration. Now multiplying the 1/4 through, this becomes 3 over 8x minus 1/4 sine of 2x and plus 1 over 32 times the sine of 4x plus a constant of integration, which is the solution to that integral. Wow, without tricks, I don't think we would have gotten there. So we write the sine to the 4th of x as the sine squared of x squared, and then we make the substitution that the sine squared of x can be written like that in terms of the cosine of 2x to the first power. We multiply this out. Now we get a square again. So to get rid of the square, we then come over here and we do a similar substitution. Instead of the cosine of x is the cosine of 2x squared. It becomes that. We substitute that in, and then you combine all the terms. Now you realize that everything is to the first power, and then you can go ahead and integrate each of these separate integrals like that. And that's how we do that. Here in this video, we're going to look at some general approaches of how to solve an integral when it's a product of a sine and a cosine raised to some power. M and n represent integers greater than 1. Now in the case if n is odd, so if the exponent on the cosine is 1 or 3 or 5 or 7 or so forth, and typically not 1, but let's say 3, 5, 7 or so forth, then what you do is you keep one of the cosines and convert each of the remaining cosine squares to 1 minus the sine square of x. So for example, let me write it down. If you have the sine, or no, in this case, if you have the cosine of 5x, then this, the cosine to the 5th power of x is equal to the cosine of x times the cosine to the 4th power of x, which can then be written as the cosine of x times the cosine of 2x, quantity squared, and then you take each of the cosine squared of x and write it as 1 minus, where are we here? Right here, 1 minus the sine square of x. So this becomes the cosine of x times 1 minus the sine square of x, quantity squared. And then if you do that, you then multiply whatever comes out of here times the sine to the n power of x, and then you have all sines of x's to various powers multiplied times the cosine of x, and that becomes your differential. So in general, if you look at this here, you take the cosine of n to the n power of x, you write as 2k plus 1. You pull out a cosine of x, and now you only have an even power to the 2nd power times k, whatever k happens to be. You write it as the 1 minus the sine square of x, and then eventually you write the 1 minus sine square of x. Well, no, that's the end product. Then you multiply everything out, multiply times this, and all of this is then multiplied times the cosine of x, and then you can integrate. If, on the other hand, m is odd, if the exponent on the sine of x is odd, then you do it the other way around. Then you write the sine of m as the sine of 2k plus 1, because it's an odd number. You then pull out a sine of x, so now you only have the sine raised to an even power. For every sine square of x, you write 1 minus the cosine square of x. You multiply this out. If this is 2, 4, 6, doesn't matter. You multiply it all out times the cosine of nx. Now you have nothing but cosines multiplied times a single sine. That becomes a differential of all the cosine terms, and you can integrate that. Finally, what if both n and m are even and none of them are odd? What do you do then? Then use the relationship to sine square of x, because remember that for each sine square of x, you can write it like this, and for each cosine square of x, you can write it like this, and you continue to simplify it until you have everything to the 1st power. Or you can use the product of the sine times the cosine and write as 1/2 the sine of 2x, and just keep simplifying that until you have nothing but the sine of 2x. Again, if you have the sine squared of 2x, then you'll have to use this relationship right here, where my sine square of x right there, to simplify it to a lower power. So that's the general technique of how to simplify these integrals so that you can integrate them. Those are the general approaches used for the product of the sine to some power of x times the cosine to some power of x. And that's how we do that.